Okay, so good evening, everyone. How was your break? Okay. Short and it's good. I think next we're gonna run through. Next we have about 5 lectures, right? So there is, in terms of announcements, there's gonna be there are going to be 2 more assignments left in terms of work, in addition to the lectures, and then you'll have your final exam. The 4th assignment is out actually, so have a look at it when you get a chance. And let's see. Okay, so just as a big picture, so now we're really moving into nonlinear methods. So basically, today we're going to look at tree methods, Adaboost, and gradient boosting. So this stuff. Oops, I shouldn't have done that. And the next couple of lectures are going to be random forests, and some, another example of a nonlinear method called multivariate adaptive regression splines. And then we'll get to support vector machines. So some of these nonlinear methods you might have already seen. In fact, even today's stuff, especially tree methods, some of you must have already seen. So if you've already seen this, then try to double up your knowledge. It should not be an easy class, right? So try to be very critical about every step, ask questions, okay, and participate in the forums. So that's what. So next 3 lectures are going to be nonlinear methods, and then we're going to go into in the 3rd lecture itself, we're going to go into unsupervised learning, basically association rules and PCA and spectral clustering. Association rules that you might have seen, market basket analysis, is a particular version of a larger idea, and we'll see the statistical view of that idea. Okay, it's like looking at essentially modes of probability distribution. Okay, so we'll look at that. And then in the last lecture, we're going to look at time series methods. And you'll actually see we have not really spent much time on talking about time series methods, because in typical workflows, what happens is you have time series data. You actually typically you create features from these from this data set, like day of the week, is it a holiday season, is it summer or winter, those kinds of features you create from your time series, and then it just becomes a supervised learning problem. Of course, you can also model it as explicitly a time series observation, where the next observation has something to do with the previous observation, and we'll see that perspective in the last lecture. Okay, so if you think we haven't covered time series, we are. Essentially, you can use supervised learning for time series. Yeah. Okay. So with that, let me talk about the learning goals for today. Okay, so tree methods, it's the first example of a nonlinear method. So you really need to kind of, if you haven't checked this, why is it nonlinear? Should be obvious by the end of first half of this lecture. And how are we optimizing its parameters? So there is this mix of both the model specification and optimizing the model together in this model family, which is a tree-based methods. Okay, you haven't seen this. For example, if we looked at linear regression, we said, okay, there's a closed form expression, or we could just do gradient descent. Okay, but first we specified the model, and then we said, okay, we can optimize it. Here we are gonna really talk about, spend some time on the optimization part of how to get a tree. Okay, tree is actually a graph, so it's a little bit of a different creature. So let's we'll look at both optimization and the model specification together. Okay. Next, there are some practical issues with tree-based methods. Some of it you might have seen before, and we'll revisit what are the practical issues, and we'll look at one version of a tree building exercise. But there are many ways to build a tree which will do classification or regression for you. So we'll look at some practical issues. Third thing is going to be what is called the general family of forward stage-wise additive models. Okay, FSAM. But one prominent member of that family is Adaboost. Okay, so Adaboost is something you might have seen before as well. Some of you who did 572. So we'll revisit Adaboost, and it's just one example, prominent example in this family of methods. Okay, which are additive methods where they keep adding some simple model in each iteration. Okay, and the last point is going to be about gradient boosted decision trees. Okay, they're also forward stage-wise additive models. So we look at how they are constructed. Okay, so Adaboost, gradient boosted decision trees, and there are other additive models as well. Okay, so any questions about the overall landscape of what we're going to do today? No questions? Okay, so let's start. So okay, so this I should have conducted a poll. How many of you have heard tree methods for like the 10th time? Okay, 2 of you have heard it for 10. Three of you have heard it for the 10th time. So how many of you have not seen tree methods before? Just one? Okay, so I'm going to be then a little bit fast on the tree-based methods. Okay, and then we can slow down towards the things which we have not seen before. So okay, so what's a tree model? A tree model is essentially just think of it as somehow partitioning the input space. By input space, I just mean, if you have 10 dimensions, there's going to be 10 features, right? And each feature, let's say, is bounded, as in like it's taking values between 0 to 1 or 0 to 100, whatever. So it's some, each dimension has some range, basically. So that collectively, I'm just calling it as input space. And tree method just partitions, not just tree method, but this whole way of thinking just partitions the input space in the sense that, let's think of 2 features. So x1 and x1 and x2. Okay. There's a bunch of methods which will just partition the input space. So what is meant by partitioning? Just break it into parts, right? So these are 5 parts, right? So this is a partitioning of the input space. This partitioning is achieved in a particular way for a tree method. Okay, that's the only I guess why it's called why is it called a tree method is the partitioning can be represented as a tree. But in general, this is a partition of an input space. And what do these methods even do? Once you partition the input space on each partition element, so there are 5 elements here, 5 regions. In each element, you can say, okay, let's say I'm doing regression. I'll give an example of classification soon. If I'm doing regression, then I'll just look at all the data points falling into each of these regions. Okay, and my model is going to just say, okay, if a data point falls into this partition element or in this region, I'm just going to predict a constant value. Okay, so what is this class of models? Even before getting into the tree model, the class of models is just going to be the number of partitioning elements. So j is equal to 1 to, let's say, j of okay. So this is just a way to say what I just said, which is just that if x belongs to some region rj, okay, I'm indexing regions, there are 5 regions, r1, r2, r3, r4, r5, and if the data point belongs to that region, just output cj as my prediction, and if doesn't belong to that region, then this indicator, or this is just a boldface 1. It just means that value is going to be 0 if x does not belong to that region, and the value is 1 if it belongs to the region. Okay, so this is the model even before getting into the tree. Okay, so we'll talk about tree methods in the next 5 minutes. This is the class of models. Okay, it's just every region, and in fact these regions are disjoint here. Okay, they don't overlap. Okay, and x will belong to some region or the other, and whichever region it belongs to, just output that value. Okay, that prediction is going to be cj. Okay, well, cj is just a number. for each region. Okay, so now tree models essentially are essentially the same as this. So if somebody asks you to write the expression for a tree model, f of x for a tree model, it's just going to be the same thing as this, where the regions are going to be regular. Okay, regular in the sense that you will see the partition boundaries as either being aligned with one of the axes. Okay, so basically here is an example. I think x1, x2, region 1, region 2, region 3, 4, and 5. Okay, so these are the 5 regions, and it's regular pattern. Okay, it's either your boundary of the partition, like this partition element, let's say 4th region, it is aligned with the y-axis, and it's aligned, one of the boundaries is aligned with the y-axis, one of the boundaries is aligned with the x-axis. Okay, any discrepancy with respect to what you have seen before so far? No, right? Okay, for those who have not seen it before, definitely ask questions. So this is the model. So we made it regular. In 2 dimensions we can actually visualize it, but in higher dimensions it's hard to visualize this type of a regular partitioning. And so a very convenient way to visualize this type of partitioning is via a tree. Okay, so the same diagram, instead of looking in terms of spatial visualization, we can visualize it as a tree where so a tree is nothing but a graph. A graph consists of nodes and edges. So this particular tree corresponding to the previous slide is going to be as follows. So so x1 less than equal to some number, let's say 5, x1 less than equal to 7, and some r3. Okay, this is the diagram for that 2D plot. 3rd region, 4th region, 5th, 2nd, and 1st. So let's say this is 5, this is 7. Okay, so this is the this is a tree visualization of the same thing. Okay, so this is the and the function form, as I said, is just this. And now we'll figure out. So we're just looking at the functional form. What do you think are the parameters of this model? Like linear model had parameters beta 1 to beta p if there were p dimensions. So here, let's say x is in p dimensions as well. So there's just a short form for saying it's p dimensional. I can write x is equal to p dimensional. So what are the parameters of this model? J is a running variable going from 1 to, let's say there are 10 regions. J is 1 to 10.
So actually, the more regions means more. So that could be one parameter, right?
Sure. So okay, capital J you're saying is a parameter. Sure, it's fine. Yeah. Any other parameters? Just a very quick question, just to warm yourself up.
I thought decision trees were non-parametric models.
So non-parametric is a misnomer. Non-parametric just means a lesser number of parameters. Yeah. So typically when people say non-parametric models, they just mean that potentially that the number of parameters scale as the data size increases. Okay, that's it's like saying instead of instead of having like 3 Gaussians describe my data, as I get more and more data points, maybe more and more Gaussians describe my data. So you could have more bumps. Like if you look at 2D data, you get more points on the more points, then maybe you can't describe it by just 3 Gaussians, like 3 bumps in the 3 peaks in the data. Like if you look at the 2-dimensional histogram or 1-dimensional histogram, maybe you need more Gaussians. So a model which can bring up more Gaussians as you get more and more data points to better reflect the data is non-parametric. But it just means it still has parameters. Okay, that's the short answer. So the parameters here are just the CJ and the regions, okay, and J itself. So if there are 10 regions, so 10 is a parameter. It's a parameter, but you can think of it as like fixed, or maybe you're not controlling it directly. CJ is the numbers that you have to assign to the regions, and the regions themselves. How are you going to describe the regions? Okay. So we'll look at one particular way of. So that was the model description. Now we are really directly jumping into optimization, which means that how do we select these regions, right? RJs and CJs, right? So these are the parameters, right? So there is a different ways to construct a tree, okay? And the way we're going to look at today is called CART. Somebody defined it, 30-40 years ago. So we'll look at first regression trees, okay? I guess the R part of CART, okay? Classification and regression trees. So we'll look at regression trees, or tree. And the regression tree, as the name implies, is going to be useful for regression. And what we ideally want to do is, if you remember, if I have a model, and let's say since I'm doing regression, let me choose square loss as my training error loss, then ideally I want to do this, right? Minimization over all the parameters. I guess let's call this theta. Okay. I mean, I'm using capital theta. Maybe I should use, it's called theta. Okay. Some bunch of things. I want to minimize this over 1 by n, which is my number of data points, sum over I is equal to 1 to n of something like yi minus f of xi square, right? This is my loss function or my training data, square loss function, and I want to minimize this. And I said that f is actually that the thing I wrote in the previous slide, which is sum over j is equal to 1 to j cj, indicator of whether x belongs to or xi belongs to, for the ith observation, belongs to that region, right? Naively, I mean, without even thinking about decision tree building and all that, details, those are details. So this is what you want to optimize for. Yeah.
And so C sub j there would be like a number.
Yeah, it's a number. It's a number per region. Yeah. So the way to think about this is there's a 2D diagram or a 3D diagram in the notes. It's basically like if your region is input is 2-dimensional, you're basically like approximating a function. Maybe the function is increasing. You're approximating it by a stepwise, like a steps, bunch of steps. Okay, so that's what you're doing. You're binning, you're breaking up it's like cutting your cake and then having a different level for each part of the region. Okay, so that's the visualization. So this is what you would like to do. Okay, so if somebody has a package for doing this, then you don't really have to care about the details of how it's optimized. But we'll just go through an exercise of how it's optimized because there will be a few choices that we can. We'll see some tricks in the process. Okay. Is this expression clear? Is it too notation heavy, or do you want examples? Okay. Did somebody say they want examples? Okay.
What does the top left mean? The set with RJ and CJ? Or how would you read that?
It's just a set of these objects. These are parameters. So CJs are scalars, right? So I mean, in a sense, numbers, right? CJs are numbers. So okay, it's a bunch of numbers, at least on the comma. So this is like But RJs are regions, and how are regions defined? They are, if they are boxes like this. The boxes like this, you can say, okay, maybe it starts at this point, but actually RJs are defined in terms of these inequalities, these left side or right side of something. So actually, for example, how is R4 defined? It's a good question. So R4 is defined as x1 being, where is this? This is R4. It's only going up to, let's say the first feature is going up to 10, and second feature is going up to 15, let's say. 0 to 15 and 0 to 10, those two features. Then R4 is defined, okay, this guy, R4 is defined in terms of these inequalities, these three inequalities, okay. So x1 being, oh, is this wrong? Did I do it incorrectly? Oh yeah, so yeah, x1 being greater than 7. So if you go to the left branch, it's less than, I mean, it's what the inequality is. So you're evaluating the inequality actually here, question mark. Okay, if x1 is less than 5, you go down this branch, and if x1 is greater than 5, you go down this branch. So here you go down the right side, so x1 is greater than 7 and x2 is less than 10. So this is the 10 level. So it's like greater than 7 and less than 10, and you know the upper bounds is like 10. So that's the description of RJ. Yeah, it's a bunch of inequalities. Okay, this is an inequality. What is it?
How do you ensure that it covered the whole region?
I start with the full region. So like if you ignore this, just look at this level, okay, and don't ignore everything below that line. Now I have the full region, which is 0 to 10 cross 0 to 15. That's my 2D space, and I split it into two parts. X1 less than 5. Okay, so x1 less than 5 plus x1 greater than 5, those two regions are the full space. So I always start with the full space. If I partition, then it's going to be the complement is always included here. I mean, the complement of the regions are included. Yeah. So this is just a way to describe, just a, same framework. It's just a function which is described in terms of these two parameters. If there are capital J regions, and you just need to optimize for this. And we'll look at one way to optimize, that is regression tree, which you've already seen. So the way you do it is you do it, and you saw the inequalities in the previous slide. They're only involving one variable, okay, which means that either I pick x1 and just look at left, is it greater or less than something, or I look at x2 and I just check whether it's greater or less than something. Okay, so in general, in this tree building process, in this particular version, I'm only going to look at whether any of the decision variable is greater or less than something. Okay, so all I need to figure out is which decision variable. I'm already using J. Okay, what should I do? Okay, let me use K. Okay, so which means that I have x1 to xp. These are my features, and a generic feature in this is x subscript k. Okay, instead of xj I used to use before. So the way we're going to start, it's a iterative procedure, in the sense that I'm going to keep repeating some steps. Okay, I'm going to start with so in each step, what I'm supposed to do is just pick a variable. So one of these x1 to xp's. So let's say I pick xk, a generic one. Okay, and I need to figure out what is that level at which it's split. In the sense, I just need to create a node which says xk less than or equal to s. Okay, and so that the right side will be xk less than or equal to s, and the right side will be xk greater than or equal to x. Sorry, greater than or equal to s. Sorry. Okay, so I just need to pick which feature and where to split. Is this clear? Okay. So the way we're gonna do it is, we have only p features, so we're gonna do it literally exhaustive search, which just means that we'll look at the first feature. For each feature, we need to figure out where to split, right? So let's say we are just doing it in a grid search manner, which just means that, like in this example, let's say I pick x1 to be my feature of interest. I need to figure out where to split. Okay, I'll just break my region, my range of x1 into equal parts, let's say 100 parts, and just evaluate. I've already picked the feature first feature. I just want to figure out where to split. I've broken into 100 parts from 0 to 10. So just 0.1, 0.2, 0.3 all the way to 10. So those would be my split choices, and I'll try to look at some criteria for this feature selection and for this split. What is that criteria? Is it look good or not? If it looks good, I'll just choose that as my splitting choice. Okay. So the criteria for regression is just going to be the following. So let's go to this example. So the region 4 came about because I have this inequality, right? So that inequality gave a region 4 and a region 5. So each split is going to give me 2 regions. Okay. So, and I start with a region. Each split gives me 2 regions, and you can see that for region 4 and region 5. So this one and these two. Okay. Let me draw that again. So that region 4 and region 5 were part like this, right? So this was region 5 and this was region 4, right? I mean, there was a full picture. Okay. So region 5 and region 4 were split from a previous region, and that previous region was this region. There's no name for that region, but that was just the union of, or just put these 2 regions next to each other, and that's the original region which got split. Okay. And the optimization, the split choice. So let's say I in this case I picked x1 as my feature or split. What I'm going to do is, and let's say I have feature 1 and a split value s. Okay, that inequality thing. For that, the performance criteria, or how good the split is just a simple thing, which is minimization over some number c1. Okay, actually let me use c4. Some number c4 of sum over xi belonging to region 4 of yi minus c4 square plus minimization over c5 of sum over xi belonging to region 5 of yi minus c5 whole square. Okay, so these were just the least square, the square loss criteria. And all I said is, okay, look at all the points belonging to each of these regions, and I just want to find these 2 numbers, because I need to, my model has to have 2 regions and also has to have a number for each of the regions, right? So the numbers, let's say, are, if these regions were the last regions, I'm not further splitting them, then there has to be numbers on those regions. So those numbers would be c4 and c5 for the region 4, region 5. Okay. But even beyond those numbers, this would be the criteria of how good that split is. Okay, so if you, this depends. Region 4 depends on s, and region 5 depends on s, in the sense that the s value determines where that split is, right? So if I've already been given the first feature and the split s, then the regions are defined. These 2 parts. Okay, this is the split. x2 less than or equal to 5. Was it 5? I think 10. Yeah. So the s value was 10 here in that example, and you just get this number. You have data, and you don't know c4 and c5, but you can figure them out by minimizing this. Okay, and you get the score. And you can get the score for feature 1, s is equal to 11, s is equal to 9, s is equal to 8. For every choice, you can get a score and pick the split that has the lowest score. Is that clear? Yeah.
And so C4, C5, like the mean of the data that's in that region?
Great question. Yes, it is the mean. So I wrote it in a very laborious, expanded way, but you can directly see this. So C4 is only involved in the first term, and C5 is only involved in the second term. So these are actually 2 different optimization problems or minimization problems. And just take the derivative. If you take the derivative, you get sum over yi minus c4, right? And a factor 2 over xi belonging to the region 4, right? And set it equal to 0. Okay. I took the derivative of the square loss, and then you get C4. I pull it to the right side. C4, you can drop the 2 actually, because 2 is multiplying with the whole thing. You have C4 is equal to sum over yi divided by the number of points in that region, okay? Because C4 is also being summed those many number of times. Okay, so C4 is just the average of that, the points in that region, the y values for those points. Okay. Yeah.
What is the difference actually if you sum and do a minimization, but you did individually the minimization?
No, this was just I just motivated as a score for a given feature and a given split. Okay, I wrote it as this is the score. If the score involves some optimization problem, and I said that optimization problem is actually easy. You just put C4 is equal to this. If you put that, then the expression would be simpler, right? I don't have to write a min. I can write sum over yi minus this particular C4, which is the average of yi's in that region. You can write it that way as well. It will not have an optimization aspect there. This is a simple. So this is just an illustration showing that if you have least squares loss and this is the way you want to split, then it's an easy problem. Okay. In contrast with doing this directly, okay, this thing is seems there's no intuition here. You just want to get regions and the coefficients at the same time by minimizing least squares loss. It's kind of hard. Okay, it's going to be computationally hard unless you do something more clever.
Is it something close to like k nearest neighbors where you are doing some sort of averaging? It
is, but k nearest neighbor is a lazy algorithm. It doesn't have notion of regions. It's like dynamic. At a given test point, figure out a region, which is the k nearest guys, and take an average. Here, these are prefixed in the sense that you have 10,000 observations. Just condense them into these regions, and let's say 10 regions and 10 coefficients, and that's it. Then you have dropped the data. You don't need the data. So, and then you just use the test point belonging to whichever region. Just output the coefficient corresponding. The c value corresponding to that. It's not like a nearest neighbor, but there is some similarity. Yeah. Yeah.
So to find the minimum, you've taken the derivative with respect to y?
No, with respect to C4. Actually, there should be a negative sign. Yes. C4. C is the variable, right? So that's what I want to figure out there. Y's are data. Good question, actually, because derivative is going to become important in the gradient boosting stuff. So if you are concerned about the sum, drop the sum. You have a something a minus b the whole square. I'm asking the derivative with respect to b. It's minus 2 times the a minus b.
Wouldn't a constant come out of that too as well?
No, it's like a minus b the whole square. Derivative with respect to b is minus 2 times a minus b. That's it. And I'm setting it equal to 0 because with minimization and maximization, ideally the minimum point is at a place where the first derivative is equal to 0. So here a was yi and b was c4.
I still get the calculus. I thought you would multiply out if you were going to take the derivative of a minus b squared.
Yeah.
It would be
with respect to b. With respect to b. So it's a derivative of a function. So we are not expanding that out. We can expand it out and you'll get the same, right?
Okay.
Guys, yeah.
Is there a criteria for which split will be made first?
Which split will be made first? So that's what. So there are so many choices, right? In the 2-dimensional case, I was not sure which feature to pick first, and in each feature I did not know what split point was there. But I'm just saying exhaustively grid search. For every pair, just get the score, whichever score is the high, lowest in this case. Just that's your split direction, as in split feature and the split point. So it's exhaustive. There could be more clever methods. So this is just an example of getting an intuition for optimization, because you'll see that most of machine learning, so especially with these types of techniques, they have if you have a lot of data, then a lot of engineers spend a lot of time on just optimizing, as in getting the model. Okay, even getting a linear regression model, and that's why we saw lasso and ridge regression. Even if you have linear models, if you have a million features, then it's not easy to optimize that, on R, for example. So and so there are people spend a lot of time on optimization. So this is just a way for us to understand how a tree could be constructed. There are many efficient ways to do so, many different ways to do so as well. Yeah. Any other question? Okay. So this was how you could choose a split, and once you choose a split, you get two I guess baby regions, and then you continue recurse. On each region you try to again split. Okay. So how long should you do this? Up to some reasonable point. What is a reasonable point? That either you can't split anymore, which means that there is no data point to evaluate. Like for example, if there is no yi's in that region, then you can't really split, right? So what can you assign the score there, right? So you can also, so this is a way to like stop your splitting procedure. So there are many different criterions to stop your splitting procedure. One criterion could be how many points are left in my region. So before even figuring out, okay, do I need to split this with some feature and some split point, figure out how many points are there in that region, and you can do that. Okay, it's relatively easy to figure out how many of my data points are in that region. And if they're too less, let's say less than 5, less than 10, then don't split anymore. That's my, so maybe R4 has only 5 points, R5 has only 4 points. Oh, 5 and 4, okay, whatever. Some number of points, then stop splitting. Okay, that's why they were the last, they were not split anymore in that example. Okay, so once you do that, you get a tree. Okay, the tree representation we saw in the previous slide, and so you don't have an explicit control on the j. J is the number of regions that you got. Okay, I mean you would get, it's a data-driven thing, right? You, depending on how much data you have, maybe you got j is equal to 100 regions, or maybe you got j is equal to 10 regions. Okay, now if you have too many data points of this, and you got too many regions, maybe you want to prune it. You want to get a smaller tree. Okay. That's only because smaller trees are, I would say, more biased, and larger trees means more nodes or more leaf nodes are more, have high variance and low bias. Okay, why is that? Let's visualize. If a tree is not split at all, then you just have to predict a constant, okay, in that input region. That's like a highly biased model. It's like saying I don't ignore the input, just output some constant. Okay. And on the opposite side, if every leaf node has one data point and you're just predicting its label, then it's like a highly overfit model, right? So that's high variance. Okay, so you wanna, so if you end up with a tree with too many leaves, then you might want to prune it. And there are many pruning techniques. We'll not go into the details of pruning techniques. Yeah, there is a notion called I guess not example, but post-processing of a tree. So the way we constructed the tree in the previous slide, repeat splitting the regions may give us too many leaves or too many regions, and then you can post-process by what is called pruning. Okay, pruning just means somehow getting a smaller tree from a bigger one. Okay, so tree, so why is it called a tree, by the way? It looks like a tree. Inverted tree. Okay, so it's called a tree because there is no there's only one path between any two nodes. Okay, or there are no cycles basically. Okay, so for example, from this node X to this node Y, there's only one path. You have to go up and down. Okay, so that's why it's called a tree. Anyway, so if you have a tree, okay, and with regions, let's say region 1, region 2, region 3, region 4, and region 5, then you can actually prune the tree by saying, okay, I want to undo the split. Basically, now have a region here, which could be region whatever 6, okay, which is a bigger region. So that's called pruning. You're just killing some nodes and bringing up, reducing the number of regions in the tree, number of regions which describe this tree model. Okay, there is a technique which is listed in the notes called cost complexity pruning, but I don't think it's very critical. So let's move on to more interesting parts. Okay. Yeah. So this one last point about regression trees before I get to classification trees, which have slight variations, is that this we use the square laws, right? So yi minus whatever cj sum over I is I such that xi belongs to that region j squared. So this is called an example of an impurity function, okay, a node impurity function or a region impurity function. It's just saying in this region, if I choose some cj, okay, some constant, how bad is that constant, okay? For example, if my data points all have predictions in this region hovering around 10, and if I choose my cj to be 2, then it's like a bad choice, right? So this is an example of what is called a node impurity or the node impurity function, which gives me a value for node impurity, okay? I mean, okay, so let's actually jump to classification trees. Is this recap too slow for people who have already seen it? Is the recap okay? Yeah.
Yeah, I have one question. Like for regression, this could be a little bit of inefficient, right? Because if we have more data points, we need to do lots of processing.
Efficiency, computational efficiency.
Computation or splitting it into regions as you have more number of data. Because if I have, like, assuming so 2 dimension, if I have just 4 points, I can just split in like 2 or 3 regions.
Yeah.
But if I have like more number of regions,
is your choice. So you can have so when you're splitting your tree, you can have, so you know how many splits are you doing. So if you have a budget on the number of splits, then only split up to that point. So there are different ways to control complexity. This was just an example of how to get an example coefficients and regions. Okay, there are many variations, C4.5, and there are many different names for these tree building procedures. Yeah, but they're computational. That's what my previous point was, that for these types of models that you've seen, even linear regression, today's model, random forest, SVM, people are interested in like scaling them up to millions of features and potentially billions of observations. So there's still a challenge there. Okay, and also there's challenge with respect to bad data. We'll look at an example of bad data pretty soon in 5-10 minutes. Okay, what is meant by bad data or missing data and all that. Okay. Okay, let's look at classification trees. So for classification tree, for each region, so for region Rj, I'm gonna have k numbers. Okay, so which is p hat 1 to p hat k. And what are these k numbers? Okay, again this is overloaded. K is the number of classes. Okay, let me not use k. Let's say I have 3 classes. So p hat 1 to p hat 3. Okay, so in the previous case there was one c value for a region. Here I'm going to have 3 numbers. Okay, because I have 3 classes, and these naturally are supposed to tell me the class conditional. This naturally is supposed to tell me the conditional probability of being in that class if I'm in this region. Okay, and and the expression is simple, just the number of points where yi was equal to that class divided by the number of points in that region. Okay, I mean this is a very informal way to say that just count the number of points which are in class 1 out of all the points that belong to that region, and that's your roughly that ratio is your estimate for the class conditional probability. Okay, what is the probability of being in that class if you are in that region? Okay, so and let's call k of j as the argmax over in this case 1 or 2 or 3. Actually, I don't even write argmax. Let me just write it as max of p hat 1, p hat 2, and p hat 3 in this 3 class. In this 3 class example, I'm just saying pick the let kj represent for this region j which of the class index it belongs to. Okay, argmax. Okay, so now given this, I'm gonna now tell you. So we're going to maintain 3 numbers. These 3 numbers are easy to obtain. So unlike regression case where there were C's, and those C's were also easy to obtain, they were just average of the Y's. Here the 3 numbers, if somebody gave you the region, the 3 numbers are easy to compute. Just look at all the points, get the proportions. Now for classification tree, you still have to do this variable selection and splitting, right? So let's say for a so variable 1, again, the split choice S. I'm just picking some specific example here. So variable 1 and split choice S, you want to figure out how good is that choice, right? So for that, once you chose a split choice, there will be two new regions, right? So there will be 2 regions, and then for each region you can have a score, and the score can be 2 regions. Let's say R1 and R2. And I can have some score for it, right? So the score can be some score, and one score I'm going to write. Okay, the simplest score could be 1 minus p hat j and kj. Okay. I guess in this case, okay. So let's call this region J1. So okay, why there looks like a lot of notation, but it just means that the score is just going to be the misclassification error in that region. Okay, so in that region, RJ1, which were the two child regions, there were a bunch of points, and I could figure out which class is the highest, has the highest proportion there, and 1 minus that proportion is the misclassified points essentially. Okay. Yeah.
In the P1, P2, P3, there are the probabilities with different splitting criteria.
No, so once I choose a feature and a split, then I can get 3 numbers per each of the 2 child regions, or the 2 baby regions, right? So if I had, remember, like in that example, I had R4 and R5, right? So let's say I chose a split here, right? X2 is less than or equal to S, or some split value 10, right? Then in each region I can have 3 numbers, and these are the 3 numbers, like maybe 0.4, 0.4, 0.3, sorry, 0.4, 0.4, 0.2 in one region, and maybe 0.2, 0.1, 0.6, 0.7 in the other region.
If you have 3 classes.
If I have 3 classes, yeah. This is a 3 class example, yeah. But all 3 numbers are not very critical. I mean, all 3 numbers are critical in the sense, if I know all the 3 numbers, I can figure out what kj is, and given the kj, I can tell you what misclassification error is. But it's just, whichever proportion is the highest, everything else, 1 minus that proportion is the misclassification, essentially. So it's basically, tying back to the idea of node impurity. If my regions are, the 2 regions are such that most of the first class is in the first region, and most of the second class is in the second region, and none of the third classes are there in these 2 regions, then this misclassification scores will be pretty low, right? Yeah, pretty low, and so you want these scores to be low. I don't want to misclassify. Okay, I want to pick that threshold, splitting threshold, such that like regions are pure in the sense that they are only most of the points in that each of the regions are of the same class. Okay, and that's why these are, I guess this is called a node impurity function. Okay, so higher this number, the more impure that node is, as in it has a mix of different classes. The lower this number, the more pure that node or that region is, and it has mostly the same class. Okay, and this is misclassification scoring criteria. There are a couple of other criteria called Gini index and cross-entropy. Okay, how many of you have heard of Gini index? Okay, it's we don't really want to go in and get in the formula for that, because I'm already writing too many expressions. So so Gini index and cross entropy are essentially very similar in behavior to the misclassification function. Okay, so there's a diagram in the book, sorry, in the notes as well as in the books. If I have two class classification, so I only have p hat 1 and p hat 2, okay, two classes. So this means that p hat 1 plus p hat 2 is equal to 1 because they're proportions, right? So I don't have to think of, it's really not 2 dimensions. I don't have to think of 2 numbers. I can only think of 1 number because the other number is 1 minus that. Okay, so if I and both of these numbers are between 0 and 1, right? These are proportions. So let me pick this guy, p hat 1, okay, between 0 and 1, and so it turns out that the misclassification error or misclassification function looks like this. Okay, depends on the proportion. If the proportion is 50%, p hat is 50%, then 50% are misclassified, right? So that's this 0.5 value on the y-axis. And when I said that these functions have the similar behavior, Gini index is also, it's something like this. It has a specific functional formula, but that's not very important. It's just it's basically when the proportion is between not close to zeros or ones, it's high, and if it's close to zeros and ones, it's low. Okay, that's just what the function is interpreted as. Okay. Any questions? So next we'll get into issues with trees. Okay, so oh my god, okay, issues. So trees are good for, especially for continuous variables, continuous features. Trees are good. I know it's a good nonlinear model. And by the way, I didn't emphasize this, but it's nonlinear because the regions are like piecewise constant regions. Okay, there's a sudden shift between regions. There's a region boundary, and between that there is no nice transition. It's like nonlinear. Okay, steps, and they can go up and down. So it's not even it's not like a line or hyperplane. So issues. The first issue is if you have categorical features. Okay, if you have categorical features, then how do you make a split, right? So far I've been showing some inequalities, x1 less than some 10 or something, but that may not be true. Your feature may be categorical, dog, fox, or cat, let's say. Then you can split that categorical feature in many ways, right? So you can put dog, fox, and cat. You can put these two together and this separately, or you can put these two together, or you can put dog and cat together and fox separately. So there are different ways to split, right? So so yeah, these are the 3 different ways to split if you only have 3 categories. But if you have more, there is some exponential dependence on the number of categories essentially. Okay. So if you have categorical features like this, so just with one feature, you have 3 split choices. So this kind of influences. And if you had a categorical feature which had 100 categories, and if you had another categorical feature which had just 2 categories, then there's going to be so many splits to consider for one category versus the other. Okay. So there's going to be some issue of you not being able to figure out, you may be always splitting on the feature which has too many categories potentially. Okay. So, but it's fine. I mean, even if you have categories, you can split. It's just that there could be some you may be spending most of the time in figuring out how to split categories, how to split categorical features than on continuous features, because continuous features you can just if you have a range from 0 to 10, you can just break it into 10 parts or 100 parts, and it's going to take 100 tries. But if your categorical variable with 100 categories, then it's 2 to the power 100 or something, 2 to the power 99. Okay, which is too many choices to consider. Okay. So second issue is it's not an issue, but aspect. So in the previous tree construction, we were splitting only what you would say as a binary split, which means that I'm only splitting some feature, so x1 let's say less than equal to s or greater than equal to s or something like that, right? So instead of binary splits, you can actually split a region into multiple parts at the same time. Okay, you could always do that, right? But it turns out that if you split let's say 3 into 3 parts, okay, 3 parts just means x1 in one region, sorry, x1 less than s, some threshold, between 2 thresholds, and above the threshold. So if you split into 3 parts, then you can get a tree which has not 2 regions as childs but 3 regions as childs, okay, children. So if you can do that, but it turns out in practice that it kind of overfits very quickly. Okay. And you can also do something else, which is why should I pick a particular feature to split? I can always split as sum over some alpha k xk being less than equal to s, where I just mean some sort of k is equal to 1 to p. So just think of k as that feature index. So all I'm saying is, instead of picking one feature and figuring out left or right, I can have a split like this. In that region, figure out a hyperplane or like a line, like maybe instead of, so that previously we were splitting into R5 and R4. I'm saying the same thing, you could split it like this. This could be R5, this could be R4, right? So this type of a line would be expressed as x1 some 5 times x1 plus 6 times x2 is less than something, right? So you could do this, but this just complicates. I mean, you could do this computationally. Okay, there's nobody's gonna stop you. But the problem, so I guess the problem that's listed in the book is that if you do these types of splits, you can't really interpret the tree. Okay, one big advantage of having a tree model is that it's nonlinear, but it's at least a single tree is definitely interpretable. You can figure out, okay, I classified somebody as somebody for not getting a loan. I can tell, okay, maybe this person has some high risk or has lower income for this loan. So you can see where the splits happen. Okay, so it's interpretable in that way. The third thing is stability, and this third thing is stability or robustness to creation of the tree, by which I just mean that if you have data which has some corruptions, as in some incorrect or noisy data, okay, some numbers were defaulted to some high or low values, then your initial split will be like completely off. Okay, so you can imagine if I had a data point like really far away in regression tree, then is it far away? Okay, if the, like for example, if y value is off or the x value is off, then your regions will be pulled away because of those points. Okay, will be deformed because of those points. So that's a usual issue with even linear regression actually. So for example, people are working even today of how to do linear regression when there are arbitrary corruptions in the data. So if I give you 1,000 rows of a table and arbitrarily change some numbers in some of the rows, how do I still get the beta hat which was the ground truth? People are working on research for that. Okay, so stability or robustness. And stability is also due to this greedy procedure. So I just said, okay, split according to one variable at a split point, again split the subsequent regions. It's a greedy procedure. Okay, so that can have, if you initially make a wrong split, then you're completely off in terms of the good model that you could build for your classification problem or regression problem. Stability or robustness. Fourth thing is smoothness. It's not really an issue with tree, but if you are really, if your underlying data, classification data or regression data had really a nice linear separation, for example, in this one-dimensional data, right? You could have a decision boundary like this, okay? But then your, what is this? Your tree model would be like blocks, right? So it would be, split it this way, something like this. So it just doesn't capture smoothness because it's literally there's boundaries and they have to be axis aligned essentially. Okay. And so those are some of the issues. Let's get to, so any questions about issues? Issues as in concerns that you need to think about when you build a tree model. Okay, things that you need to think about. Any questions? Okay, so let's look at missing data. So why we're transitioning to this topic is because we need to kind of, at some point we need to understand, okay, we don't have clean data, which is always almost the case. Okay, if you have clean data, that's suspicious. You may have suspicious some selection bias or some really something else going on. Second thing is missing data, and especially tree models, there is some nice way to at least take care of missing data in tree models. Second thing is there are different ways to have bad data. Missing data is one, where a lot of NAs or NANs, whatever, in your tables. But there's also the previous thing I mentioned, which is corruptions or noise. I mean, it's not really noise. It's like arbitrarily some entries are completely off. Like if you take a survey, I mean, you collect a survey results. Okay, some people may be randomly filling it out, right? So that's gonna bias or completely change your inference or whatever conclusions you're deriving from that type of data. Hopefully, if there are not too many, okay, then you can fix it somehow. Okay, and that's what I said was is kind of still of interest to researchers in machine learning these days. But today I'll just talk about missing data. Okay, so one example, is a selection bias. Okay, and this is example in the notes as well. So let's say you make physical measurements of athletes who compete in the Olympics, or for example, then their measurements would be so you make measurements for these athletes because they keep taking measurements, so it's easy probably to get their measurements of height, weight, and so on. Okay, but you kind of ignore the fact that these were Olympic athletes, and you have this data, and then you look at means and all sorts of descriptive statistics or do inference on that. Then that's going to be off, right? So here the missing data was the column which said these guys are athletes, right? So that's just selection bias. But there are a couple of other biases which kind of tie back to how you could deal with them. For example, some of you must have done imputation. Some of you must have heard of imputation, where if an entry is missing, I can fill it up with some other number. Okay, so when is that a valid operation to do? Maybe we can conclude. We'll figure that out in a couple of minutes. Okay, so what are some two other missing data settings? One, and there are some phrases for them or setting. These settings have names. The first one is missing at random. Okay, and the second one is missing completely at random. Okay, so the way we think about these two settings is follows. So let's say we have the X matrix. So it's the data with rows being my observations. Okay, and the Y data, let's say it's a vector. Okay, n cross 1, n cross p, right? So if that is our data, then let's say we are missing some entries. So NA, something like that. Okay, some entries are missing. Now this locations of missing entries, I can encode it as a matrix, right? I can say R, which is a 1 over there, 1 over there, and 1 over there, maybe zeros elsewhere, right? I can say this is the locations where things are missing, right? Then missing at random. Okay, so missing at random just means that the probability of R. So we are gonna think of this R, this matrix R, as some way of is the missing pattern, right? So we're gonna ask whether this missing pattern has something to do with the observations. Okay, if the missing pattern has something to do with the observations, then there is some bias. Okay, so probability of R given the data, that the X matrix and the Y matrix, okay, is equal to, in both cases actually, P of R given X matrix and Y matrix. So let's take the simpler case. Missing completely at random means that P of R given X and Y data has nothing to do with the data. It's just probability of R. Okay, in a sense, it's missing completely at random. So it's as if you had clean data and somebody randomly flipped coins and dropped some entries. Okay, there's not gonna in this case you could probably impute in the second case. Okay, and you would get away with imputation. See, first of all, you've not observed the entry, so you can fill in any number there. What is the most plausible thing is you can impute, as in pick a mean value and all that. So you've seen that in empirical in a workflows, right? But this is a nice case to have where you're saying that the data had nothing to do with it being missed. Okay, it being not there. Missing at random means that the locations that were missing, it doesn't depend on the values at those locations. Okay, it depends on the values that were actually collected. So by which I mean depends on PR given X observed and Y observed. Okay, which means that it doesn't. So this NA locations had some values, right? We don't know those values. All I'm saying is that the missing pattern doesn't depend on the value. Okay, so here is an example. What is the example? Yeah, so this is a good example. So if a patient's sickness measurement was not taken because she was too sick, okay, so that's an example where it's not missing at random. Because that particular person was too sick, you didn't take the measurements. Okay, so that doesn't fit into the missing at random version. Okay, it could be, that's an example of things where you are missing it because of the data point at that location itself. So that's not under any of the settings. That's selection bias actually. Missing at random would be I'll have to think of it and I'll come back in the break. After the break, maybe I'll tell something. I don't want to give a wrong example. Okay. So these are some aspects of missing data. Okay. So we haven't seen. I mean, there are many other ways that data can be bad. Like this is actually a big item. But missing data, these are the settings. Actually, missing completely at random is where imputation is a mild thing to do. If you're missing at random, imputation is still iffy whether you can allow to do imputation or not. Okay, selection bias is definitely a bad situation. I mean, as long as you know what the bias was, you can say under these biases, it's something is maybe your inference descriptive statistics are correct, then that's fine probably. Okay. Okay. Any questions about this tangent? This thing about missing data? Okay, so next let's look at okay, so now let's look at next set of nonlinear models. Okay, so forward stage-wise additive models. It's a mouthful, but it just means that, and we'll actually start with Adaboost, which some of you may have heard of. Okay, so this is the second nonlinear model that we'll look at today. So what is the model here? Okay, what is the f of x? So let's start with Adaboost. So Adaboost actually stands for adaptive boosting. Okay, there's some and actually .m1 is the actual name for that algorithm that the inventors gave. So what is the model? Okay, the model is f of x is equal to sine of sum over m is equal to 1 to m of f alpha m fm of x. Okay, so it's for binary classification, and that you can see by saying f of x is a sine of something. Okay, sine of a number. So this things inside I'll tell you, but that the summation inside has to evaluate to a number. The number is positive, then f of x is positive class, and if the number is negative, then f of x is a negative class because it evaluates to plus or minus 1. Okay, so binary classification plus or minus 1, plus 1, minus 1 instead of 1 or 0, slight difference, but this is the two classes. And for this, the Adaboost model assumes that f of x is like this. Okay, now these alpha m's are some numbers. Okay, so they are again numbers, scalars. fm is indexed by indexing variable m. So let's say there are capital M is 10, let's say, then there is f1, f2, f3, all the way to f10. So these f1 to f10 little f's, these guys are what are called weak classifiers. Okay, so we're going to focus on classification now. Okay, we can see regression later. So these are called weak classifiers. Yeah, and weak classifiers just mean that these classifiers have very relatively high misclassification errors. Okay, or they are not really good classifiers basically. So like 60%. So if it's binary classification and data is balanced, then you would think that okay, a bad classifier is random guessing. So you just flip a coin, guess positive class or negative class, and your performance would be 50%. Okay, but these classifiers are just barely above that number. Okay, so their accuracy could be 60% or 55% or something like that. Okay, and so that's the structure of the model that we're going to construct, and we're going to again construct it sequentially in an additive way. Okay, so additive part comes from this summation here. Okay, this sum over m, and stage wise is because we're going to add one model at a time. So learn one model at a time. So learn the parameters of each model at a time. So these are weak classifiers. They'll have their own parameters. Let's call it theta m for the mth model. Then you learn that parameter for the mth model, and then go to the m plus 1th model, learn its parameters, and then m plus 2 learn its parameters, and so on. Okay. Yeah, so let's look at it, what's happening figuratively. So you start with some training data. Okay, so let's call it data 1. Okay, that's the starting point. I have some data. What I'm going to do is fix from that data I'll build a model f1 of x. Okay, that's for m is equal to 1. Then I'm going to use the data and this model to figure out a data 2. Okay, there's going to be some slight change in this data, so I'll tell you what the specifics are, but at the very high level block level structure, you have data from which you could build this. First model is easy. The next model is going to be is also easy. It's going to be on slightly modified data. Okay, and I'll tell you what the modification is pretty soon. I'll get f2 of x, and then again use data 2 and this built model to get data 3 and so on. Okay, so from data 3 I'll get f3 of x and so on. So if I have 10, if capital M is 10, so I'll create these 10 models, but each model is being built from a slightly different data set. And what do I mean by the different data set? Okay, so typically, let's say my P is 3, so I have a 3-dimensional data set. Okay, let's say my data is 1, 2.5 minus 1.32, 0.6, 1.35. Okay, so let's say actually 0.4, 1, 2. Okay, so let's say these are my 4 observations. So when I said I modify my data set, I'm going to maintain what are called weights for each observation. So for the first observation, there will be W1, W2, W3, and W4. So four observations, 4 weights, and this data set with the features and of course the y's. There is going to be a bunch of y's, right? Let's say 10, 5, 4, 1, some numbers. The data set is going to consist of not just the x comma y's but also the weights. Okay, so there's one additional bunch of numbers that I keep. Okay, that's my data set now, and I'm going to keep changing these weights, and that's going to give me different data sets. Okay, is the what is meant by data 1, data 2, data 3 clear? There's going to be a slight change in the weights. So the features and the y's are the same, but weights change. Okay, and the way they change, intuition first, is that I built my first model, right? So I built my first model. I didn't, that didn't need anything else. I just used my data with some weights. Let's say the weights are all equal to 1 by n. Okay, for simplicity, some constant, doesn't matter. So I built my model using that data, and now that model made errors in some observations, maybe really predicted well some other observations, right? So it could have done well in some observations, might not have done well in other observations because it's a weak classifier, right? It could also be a good classifier, in which case it would not have done well in very small subset of points. But wherever it did not do well, you're gonna increase the weights of increase the weight numbers for those observations. Okay, so let's say the classifier didn't do well on these 2 points, then these 2 weights, starting initially they were values 1 by n or 1 by 4 in this case, 4 observations. Those 1 by 4 numbers, 1 by 4, 1 by 4 would be increased up, okay, in some specific way. Okay, so we are increasing the weight of those observations which were misclassified before by my current classifier, which is F1. Okay, and that gives me F2. So with the modified data, that gives me F2. So I haven't told you how I'm getting a F model from weighted data. That I'll tell you right now. Yes.
That's what
okay, so it's actually a very simple trick, and people must have heard of cost-sensitive classification or weighted versions of. So when you have imbalanced data, you weigh the smaller class up and bigger class low. So I'll tell you. So what am I going to do with this weight? So basically, when I build a model, so let's say f2 of x, right? So f2 of x is okay, minus yi xi squared times wi sum over I is equal to 1 to n. So let's say I'm doing actually I'm doing classification, but I can also use square laws for classification, but I'm also using y's here, but doesn't matter. So weighted, I'm going to use the weights in this way. I'm just going to, there's going to be a loss term for each observation. I'm just going to multiply it with the weight. Okay, so if the weight is high, you better not make a mistake for that observation, right? If the weight is like 0, that observation doesn't even count because there's no loss if I completely gave a garbage answer for that, garbage prediction for that, right? So that's all. That's how I'm going to use weights, and it's actually useful for imbalanced data sets as well. So if you have a positive class there are only 5 positive examples and a million negative examples, then you want to put a weight for every time you make a mistake on the positive class, make a wrong prediction, you incur a huge penalty. So your trade-off is that you'll probably make more mistakes on the on the bigger class potentially. Okay, so there also the metrics change. You don't really care about accuracy too much. You care about what are called type 1, type 2 errors or things of that nature. Yeah.
So the weights are not related to the independent variables, but just to the specific observations, right?
Yes, they are not feature related. They are observation related. You could also have feature related, so you can come up with your own model with feature related weights and changing them and so on. Yeah, good point. So this is it. So this is how you would build that second model, and once you know how to build a second model, third model is also simple. So what I've not told you is how I'm going to update the weights. That's the only thing remaining, right? So the weight update is, as I said, intuitively we already said how it's going to be updated. If that observation was not correctly classified by the current model, then the weight has to be increased, right? So yeah, so the way I don't think there is too much intuition to be gained, but Adaboost, so Adaboost changes the weights in this way. So if something was misclassified, then the weights are increased by some number alpha. So let's say I'm in the first model. So in the first model F1, misclassified some observations and correctly classified some observations. Okay, so the ones where it misclassified, I'm gonna multiply with alpha 1. So if I was misclassified, okay, so I mean why this multiplication factor is because e to the power 0 is 1, right? E to the power any other positive number is kind of bigger than 1, right? So what is this? So what is this parameter? So alpha 1 is somehow related to. It just depends on. Let me just say depends on misclassification error. Okay, depends on overall misclassification error. All I'm saying is F1. I built an F1. I minimized some loss, maybe 0, 1 loss or something else or a square loss. I got the F1. I got the loss value score. Okay, just think of that as the instead of misclassification, you can think of that loss value as some score. Okay, and alpha 1 is some simple transformation of that score. Okay, or you can just think of that score itself. All I'm saying is if I was misclassified, then I multiply that weight by a number which is e to the power, again a slight transformation of that score. Okay, just to keep things positive and ensure that numbers are not getting weight is not decreasing. That's all. The e to the power thing is just to ensure that the weight is increasing if I'm misclassified that observation. Okay, that's it. So given these descriptions, the Adaboost is description is complete. You start with a simple weak classifier. Misclassify, you don't want to purposefully misclassify anything, but you may misclassify some points, upweigh those points, build another classifier, get another classifier from the same class, potentially, or different class, doesn't matter, and with this weighted loss function like this with weights, and again see misclassification. On those misclassifications, again the weights will increase potentially, right, and so on, continue up to some predetermined number of steps, or till you're not seeing any improvement in misclassification, overall misclassification error rates, for example. Okay. Any questions about Adaboost? Yeah.
Say at the first stage, I conclude that only W3 and W4 has to be increased.
Yeah.
But after that, I see even W1 and W2 has to be increased.
Yeah.
So will there be some sort of like feedback effect or something like that?
There could be, yes, good point. Yeah, you could probably just be upweighting both of them and then have a feedback loop which sends all the weights to infinity. You can have it can happen. I mean, this is just I'm giving you an answer off the fly, but it can, from what I've described, yeah, there is no restriction for that. Yeah.
So till we come to that final stage, like if you say 5 stages and it like 5,
Yeah.
I cannot actually correctly say what will be my weights, right?
I mean, weights are just needed for me to change the data. I don't care about the actual values of the weights, right? In fact, we are proportional. I mean, whether they are 1, 2, 3, 4, or whether they're 2, 4, 6, 8, it doesn't matter. I mean, what is your question exactly?
No, my question was initially you said, right, like W1, W2, they printed well with those weights.
Yeah.
But I think 2 data points.
Yeah. So let's say these two are wrong, then these weights will be increased.
So next iteration,
Yeah.
I found like the first
Yeah, the first two can be misclassified, then their weights will increase. Yes, I agree. Then.
Oh, okay. That's what.
Okay. Yeah. Any other questions? Okay, so I think it's a good time to take a break, and we'll revisit at 7:35.